Now let us look at the following theorems. The first one is the redundant literal rule. It says if we have A plus A complement B, it can be written as A plus B, right? And if we have A dot A complement plus B, it can be written as AB. So there are two ways of proving this kind of theorems. Either we can use the Venn diagram to prove this theorem, or we can use the switching algebra expressions to prove this theorem, or we can make a truth table for this. So what I will do is I will try to prove these theorems with the help of the truth table. Okay. So the first theorem is the redundant literal rule. It says if we have A plus A complement B, it can be written as A plus B. Let us try to make a truth table for this. We have A, we have B. Let us try to find A complement. Then we will try to find what is A complement B. Then we will try to find what is A plus A complement B. Okay. So what are the combinations? They can be 0, 0, 0, 1, 1, 0 and 1, 1. So what is A complement? A complement can be written as 1, 1, 0, 0. What is A complement B? That means we have to make AND of these two, A complement and B. So their AND will be 0, 1, 0 and 0. And then what is A plus A complement B? That means you will going to apply OR between these two. So the OR will be 0, 1, 1, 1. This is 0, 1, 1, 1. Now if we make A plus B, so assume this is A, this is B, and this is A plus B, right? So their combinations can be 0, 0, 0, 1, 1, 0 and 1, 1. Then A or B is 0, 1, 1, 1, right? So as you can see, this and this both are same. So we can say left hand side is equal to right hand side, hence proven. Right? Right? So we can also visualize this with the help of a Venn diagram. So how can you visualize it with the help of a Venn diagram? Assume this is the universe. This is denoting A. This is denoting B. Okay. Then what is A? So A is this much. This complete is A. This complete is A, right? And then what is A complement B? A complement B is the part of B which is not in A. So this is the part of B which is not in A, right? Right? So, and then what is A plus B? A plus B is basically adding this part with this part, right? So as you can see, if it is A plus A complement B, then obviously it is equal to A plus B with the help of this diagram, right? So it is a very simple thing to prove, right? So next is A dot A complement plus B is equal to AB. As you can see, this is just a dual form of this, but still we can try to prove it. So you can see here, if we take A, assume this is A, this is B, then their combinations can be 0, 0, 0, 1, 1, 0 and 1, 1. And let us try to find what is A complement. So A complement can be 1, 1, 0, 0. Sorry, it is 1, 1, 0, 0. I should not have written it here. And then what is A complement plus B? A complement plus B is 1, 1, 0, 1. And then what is A dot A complement plus B, right? So you have to make AND of between these two, and between these two, okay? So AND will be, this is 0, 0, 0, 1, right? And let us try to find AB. What is AB? If this is A, this is B, and this is A dot B, then AB is 0, 0, 0, 1, 1, 0, 1, 1, and this is an AND operation. Therefore, we can say it is 0, 0, 0, 1. So as you can see, this value, this and this both are actually equal. Correct? So you can see we have just proved the redundant literal. rule. Now let us try to prove the absorption law after this. Now let us try to prove the absorption law. So what is the absorption law? It says if we have A plus A dot B, then it can be written as A, right? So there are two ways. Either you can prove it using Venn diagram. So let us try to draw a Venn diagram. This is the universe. Assume this is A, this is B, right? So what is A dot B? This region is denoting A dot B. So we can say we are selecting this region and we are selecting the complete A, right? As you can see, this is just covering the complete A. So we can say A plus A dot B is equal to A. It is very simple to visualize this way, but let us try to prove it using the truth table. So we have A and B, and this is A dot B. We can say what is AB? 0 0 0 1 1 0 1 1. A dot B will be 0 0 0 1, and then what is A plus A dot B? That means we are doing OR between this and this. So OR will be 0 1 1 1, right? Sorry, 0 0 0 0 0 1 1. So which is actually equivalent to A itself, right? So we can say the absorption law holds in this case. So next is A. The next part of absorption law is A dot A plus B, which is equal to A itself. This is just a dual form of this, as you can see. So we can say in this case, if this is A and this is B, right? So the combinations can be 0 0 0 1 1 0 and 1 1. Then what is A plus B? A plus B can be written as 0 1 1 1, and then what is A dot A plus B? It can be written as, so we can say it is 0 0 1 1, so which is equal to A itself, right? Therefore you can say the absorption flow holds in this case also, correct? Now let us try to prove the consensus theorem after this. Next is the consensus theorem. So what is the consensus theorem? It says if we have A, it says if we have AB plus A complement C plus BC, it can be written as AB plus A complement C, right? So we can prove it using the truth table, but that will be a very long method. But instead of that, we can just use identities of switching its algebra for this. So this is the left hand side, LHS, and this is the right hand side, RHS. Now let us take the LHS. This is left hand side. So it is AB plus A complement C plus BC, right? So how can you prove it? We have to make this left hand side equal to right hand side. So you can say it is AB plus A complement C plus BC dot A plus A complement, right? So which is equal to 1, right? So you can say it is very simple to understand. Why I am doing this? Because if you see, BC is equal to BC dot 1, right? So B dot C is equal to BC dot 1, and instead of this one I can also write BC is equal to BC dot A plus A complement. It is very easy to understand in this case, right? So you can write it as AB plus A complement C plus ABC plus A complement BC, right? Now between these two, this one and this one, you can take AB as common. Between this one and this one, you can take A complement C as common. So it will be AB, which is 1 plus C plus A complement C, which is 1 plus B. So it is equal to 1 itself, it is equal to 1, right? So we already know this. If you do A plus 1 or any one expression plus 1, then it is equal to 1 itself, because OR is going to make it as 1. So it can be written as AB plus A complement C, which is equal to the right hand side. Hence the consensus theorem is proved, right? So this is, you can say this is just a dual form of the consensus theorem. So let us try to prove it. So it says it is A plus B dot A complement plus C dot B plus C is equal to A plus B dot A complement plus C, right? So this is the left hand side, this is the left hand side, and this is the right hand side. So let us try to make left hand side is equal to the right hand side. So LHS is a plus b dot a complement plus c dot b plus c. Try to expand it, so it will be a dot a complement plus ac plus b dot a complement plus bc dot b plus c, right? So it can be written as 0. So it is 0 plus ac plus b dot a complement plus bc dot b plus c, right? So you can eliminate it. So it can be written as, try to expand it again. So it is abc plus b dot a complement plus b dot c plus a dot c plus a complement b dot c plus b dot c. So you can say it is equal to b, this one. Here again it is repeating itself, here again it is repeating itself, here again it is repeating itself. So it can be written as abc plus a complement b plus bc plus ac plus a complement bc plus bc. It is very simple to understand. So from this you can take something as common, take this one and this one, you can take bc as common, so it is a plus 1, right? Take this one and this one, you can take a complement b as common, so take a complement b as common, so it is 1 plus c, right? Plus we have ac, right? Plus one more thing, if it is repeating itself, it is bc plus bc, then you don't have to write it twice, you can just write it once, right? So there is no benefit of writing it twice. So we can take it as, you can just add it, we'll check it later on. So bc, so this is 1, this is 1, so it is bc plus a complement b plus ac, and this is equal to bc itself, so it is bc plus a complement b plus ac. It is very simple to understand in this case, right? Now let us take the right hand side. So right hand side is, what is the right hand side? It is RHS is a plus b dot a complement plus c. It can be written as a dot a complement plus a dot c plus b dot a complement plus bc, which is equal to, this is 0, so it is ac plus a complement b plus bc, right? So here also we are getting ac a complement b plus bc, here also ac a complement b plus bc, right? So the right hand side is equal to the right hand side. So this consistency theorem is also proved. Now let us try to prove the transposition theorem. So let us prove the transposition theorem. It says we have ab plus a complement c, it can be written as a plus c dot a complement plus b, right? So let us try to prove it. Let us take the left, we have the left hand side and the right hand side. Let us try to take the right hand side first. We have right hand side, it says a plus c dot a complement plus b. So it can be written as a dot a complement plus ab plus a complement dot c plus bc, which is equal to, this is equal to 0. So it is ab plus a complement c plus bc, right? So this is the right hand side. Fine. Now let us take, with this bc I can write ab plus a complement c plus bc a plus a complement. So it can be written as ab plus a complement c plus abc plus a complement bc, right? So in this case we need ab and a complement c. So you can take ab as common between these two and a complement c as common between these two. So it will be ab into 1 plus c plus a complement c into 1 plus dot 1 plus b. So it can be written as ab plus a complement c. As you can see, this can be written as 1 and this can be written as 1. So it is very easy to understand. Fine. So now let us try to prove more theorems in this case.